In the Department of Polymer Chemistry of Vilnius University, we have long experience and facilities for the synthesis and structure characterization of hydrophilic brush polymers. Brush polymers carry long side chains and charge-containing units or units with catechol groups that allows strong binding to different surfaces. Brush polymers are particularly useful for surface modification, providing aqueous lubrication, reducing friction between two surfaces, increasing biocompatibility, and reducing non-specific protein adsorption.
Some brush polymers could change their conformation in solutions under applied of external stimuli, such temperature or pH, and have high potential to be applied as selective draft carriers. Such polymer-modified nanoparticles have improved cellular uptake and can be used as promising biomarkers in cancer diagnostics.
For more than a decade, the sector of applied biocatalysis at Life Sciences Center has been working on the development and applications of biocatalytic systems. One of our research fields is widely used polymer polyurethane. We are investigating its biodegradation and its synthesis using bio-based compounds. One of such compounds is polyol. We have created a chemoenzymatic method according to green chemistry principles for biopolyol synthesis from rapeseed oil and the used cooking oil. This biopolyol can be applied in the polyurethane synthesis as a component in coatings or adhesives and as a biomaterial for 3D printing. Some of these approaches has already been implemented in collaboration with Lithuanian companies.
Our Laser Nanophotonics group at Laser Research Center of Physics Faculty, Vilnius University, studies light matter interaction at spatio-temporally confined conditions and apply it for advanced 3D nanolithography. Recently, we have developed a route for production of 3D nanostructures consisting of inorganic substances such as glasses, ceramics, and crystalline materials. The method is based on 3D nanolithography followed by high-temperature calcination, or in other words, thermal treatment, which converts the hybrid polymer into fully inorganic matter. The approach is allowing 3D nanofabrication at sub-100 nanometer feature resolution. It's widely applicable in diverse microsystems with heavy-duty and high-resilience applications such as micro-optics, nanophotonic circuits, and biomedical scaffolds.